So we want a way to describe how the volume changes as a function of pressure, V equals V of P, or alternatively, how pressure changes as a function of volume as the volume grows. Last time we talked about that if I make a graph here, and I have pressure as a function of volume, when the volume of the gas expands, its pressure is going to drop. That seems intuitive, but we're not sure, will it be some very steep function like this? Will drop straight down, that doesn't seem likely. Or will it be a more gradual change like this? Well, we're going to see a few options here that we'll talk about much more when we look in more detail at thermal physics. So let's take a look at a famous equation involving pressure and volume. You probably remember from conceptual physics or physical science, or maybe from chemistry, PV equals nRT. This is saying the pressure times the volume in a gas is equal to the number of moles times the gas constant times the temperature. One consideration we might make would be if this was constant. We know we have a constant amount of gas as long as the water's in the rocket. No gas is actually escaping, it's just expanding. But we could make an assumption that temperature is constant, and then PV would be a constant. So if temperature is constant, we use the word iso, meaning same, to describe a state like this. Isothermal means same temperature. So when temperature is a constant, we could use this relationship that PV is a constant, determined by the temperature. Then we could say P initial times V initial is P final times V final, and that's when you get this kind of function that looks, well, it is a hyperbola. This sort of shape would be a constant temperature expansion. Now that only happens if the gas expands very slowly so its temperature doesn't change. But you might know if you slam a gas really hard or expand it really fast, it's going to get really hot or really cold. Whoa! This is a big part of how engines work, is very rapid expansion of gas during part of their cycle. So the relationship, if we had an isothermal equation, would be V final is V initial times the ratio of pressures before and after the expansion. However, that's not the case in our rockets. Let's take a look at a couple of our rocket launches and see how they look in terms of speed.
Oh. Oh. Oh.
Whoa!
Whoa.
Whoa!
Whoa.
So what we saw is that a cloud forms. Do you see this cloud here? There's a little, looks like a Gandalf smoke ring here behind the rocket as it's taking off. Another example, here's from a launch Owen and I did. This is a cloud, and a much bigger cloud expanding, and you can even see through the bottle. Well, you can't see through the bottle because it's filled with a cloud. Clouds happen when the gas gets much cooler during this rapid expansion. That human air, we get condensation in little droplets that form a cloud. So something's happened here. The gas has expanded very rapidly, as we saw in the video, and a cloud formed. So we know the temperature is decreasing rapidly. So we need a different equation. The equation we're going to use is P times V to the gamma. This is the Greek letter lowercase gamma, is a constant. So this is called an adiabatic equation of state. Adiabatic. Now we talked about isothermal is when expansion is really slow. Adiabatic is a description for when the expansion of gas is very fast. Both isothermal and adiabatic, these are idealizations. They're two extremes that are different ideal cases, and we're much closer to adiabatic expansion here. What's this gamma? Well, we don't need to worry right now about where it comes from or how we get its value. Just know that this is an exponent that works when gases expand very quickly, and it depends on the gas we're talking about. In our case, talking about air, gamma is about 1.4, 7/5. We'll see where that came from in a few weeks. We can say, since this is a constant, this quantity at any given time will be the same. So P initial times V initial to the 1.4 will be P final times V final to the 1.4. Now, we know that we can have the same expression we had for the isothermal expansion, except we're going to have these gammas thrown on. And since we have a gamma upstairs and downstairs here, we can simplify a bit by just pulling the gamma outside the ratio of volumes. Now, you know the volume you start with because you decide how much water you put in your rocket. Maybe you put 150 cc's, 150 cubic centimeters of water in your rocket in a 2-liter rocket. So you would have 2 liters minus 150 cc's, minus 0.15 liters as your starting volume, and your ending volume will definitely be 2 liters. So we can find an expression at any given time for the final pressure as a function of the initial pressure and how much the volume has already increased. So that's half our goal here.